Hello everyone, this is Team U1. My name is Welbeck Sinton and I have with me today Omar Alvi, Keon Bay, Eric Diamond, and Nolan Truve. And we are going to be presenting to you the heterogeneous integration of the iPhone 4S as our final project. In this presentation, we will talk about the iPhone 4S and its features. Then we will get into disassembly of the phone to look at some important components in it. We will discuss the design selections that were made in designing and packaging for each of these important components. Then area that need to be improved in the packaging technologies used. The iPhone 4S was selected because it has enough complex components and features that we can consider in the heterogeneous integration design. Some of the features of the phone include an A5 system chip, dual-core processor which runs at 800 megahertz. It has two CPU cores with a frequency of 1 gigahertz. It also has a RAM of 512 megabytes for the system memory, making it faster. It has a built-in storage space of 64 gigabytes. And like most smartphones, it has Bluetooth, Wi-Fi, and other features includes a gyroscope, light sensor, accelerometer, and proximity sensor. To begin the disassembly of the iPhone 4S, we needed some tools, including a pentalobe screwdriver, a flathead screwdriver, a Phillips head screwdriver, and a spudger. First, we remove the SIM card holder from from the side of the device by inserting a paper clip into the side hole. We then remove the two bottom and end screws with a 5-point pentalobe screwdriver, and then slide the back housing to expose the battery, the inner circuitry of the phone. In order to remove the battery, we remove the screws holding the battery connectors. Once that was done, we just pry the battery out. After the battery had been taken out, the shield covers for charge port, screen button, and connectors were removed by unscrewing the corresponding screws. With all the connectors were disconnected from the device by manually displacing them, and with all the screws removed, the logic board, that's the motherboard for the chips, were pulled out to access those important components that were needed to be examined for the heterogeneous integration. And finally, other components like the vibrator, the speaker or microphone uh, were also removed. This is the list of the various important components which we are going to discuss in the following sections. We have a dual-core A5 processor, a quad-com transceiver, Skyworks power amplifier, a Vario power amplifier, triquint surface acoustic wave filter. We also have a triquint duplexer module for radio frequencies, an ST micro gyroscope, ST micro 3-axis accelerometer, and then we have a TI touchscreen controller, and then also the Apple Audio chip.
Power amplifiers in cell phones allow them to send and receive radio signals which contain data and voice information. In the iPhone 4S, there are two power amplifiers, the Skyworks 77464 and the Avago 7781. These two power amplifiers operate on the two different major radio communication systems that exist in the world, which is GSM and WCDMA. Having both of these power amplifiers allows the iPhone to be used worldwide across a multitude of different carriers and platforms without having to, with being able to use the same phone. So with that being said, power amplifiers are essential to the overall function of the cell phone. If they fail, then you can't call anyone, you can't receive text messages, and you can't access data. Um, so it is essential that they be designed with reliability as number one priority. Uh, couple concerns with power amplifiers is that they do consume a lot of power just for the nature of the how they work. So that is a that's going to cause considerations with the thermal aspects of the power amplifier, and package designer is going to have to take into account the thermal considerations. Additionally, these power amplifiers, although they do a lot, they do have to be very small to fit on the main logic board of the iPhone. So that's also a consideration that package designers will have to take into account. Beginning at the 0th level of the power amplifier, we have found that gallium arsenide is the primary semiconductor used in the die. There are several reasons for this. The first being that the electrons have high mobility throughout the material, which means that electrons can more quickly move through the material. Additionally, gallium arsenide has direct bandgap energy, which means that the material can interface more efficiently with protons as compared to silicon. And these two combined properties of gallium arsenide result in higher device speeds as compared to silicon. Another advantage of gallium arsenide is its high resistivity, which means that it has dielectric properties. Having dielectric properties eliminates the need to deposit film resistors and insulators, which saves space, power, and most importantly, improves reliability due to the monolithic approach of not having a lot of different materials, but just one material that can do the function of several other ones. The manufacturing process of high-density gallium arsenide integrated circuits actually uses the same fabrication equipment as standard silicon integrated circuits and closely follows the same processing techniques. This approach allows for the use of well-developed, tried and true equipment and processes to ensure economical and consistent manufacturing results. Moving up in the package hierarchy, we find that the primary package choice for power amplifiers is QFN, or quad flat no leads type packages. There are several advantages to the QFN type packages. One of the biggest ones is better thermal performance, which, as I mentioned earlier, is very important for a power amplifier since they do consume a lot of power and therefore dissipate a lot of heat. Another advantage of QFN type packages is that they utilize wire bonds, which is a tried and true technology that has a high rate of reliability. Additionally, QFN type packages use epoxy resin as a die attach, which has a much better thermal performance than eutectic solder, so that allows for more heat to be dissipated throughout the chip. According to several sources, we found that the manufacturing of QFN type packages involves fewer process steps and less capital equipment as compared to other types of packages, which results in a more economical manufacturing process. In addition, the use of epoxy resin has a high throughput and uses proven manufacturing technology. Finally, the epoxy, as previously mentioned, the epoxy resin with filler is a proven technology that has a high rate of reliability, and the epoxy resin also bonds well to the lead frame. All in all, QFN packages are very reliable, small, and are very good at dissipating heat, which is ideal for the power amplifier. While the design of power amplifiers is quite robust and uses a lot of proven technology, there definitely is room for improvement and some areas of concern that I found when doing research. The first one is that gallium arsenide is a very expensive semiconductor as compared to silicon. It can easily be 100 times more expensive for the same wafer size. In addition, gallium arsenide consumes a lot of power compared to silicon. The QFN type packages has non-extending leads, which can be difficult to solder and essentially makes it so that if the power amplifier fails, you are not able to very easily replace the power amplifier. So a few suggestions that I had just by doing research is that these power amplifiers could use the same QFN type packages, but use QFN with flip chip instead of wire bonds, This would allow for more interconnects and better thermal performance. In addition, gold thermal vias could provide enhanced thermal performance since this is a very high power device, and uh, from what we found, gold thermal vias are not typically used. You could also enhance the thermal performance by using a QFN type package with an exposed die pad that's soldered to the substrate. And the last suggestion, which may be ahead of its technology, which may be ahead of current technology, is that you could use stacked chips in order to meet the WCDMA and GSM needs. Therefore, you might add a little bit in the chip height, but you are eliminating the need for an entire chip, and that will save some uh, surface area on the motherboard.
The STMicro AGD82135 LUSTI gyroscope is the gyroscope that's found on board of the logic board for the iPhone 4S. This is the same as the STMicroelectronics L3G4200D MEMS gyroscope that is available commercially. This device is a low-power 3-axis angular rate sensor. As you can see in the diagram on the right, this sensor is concerned with determining the yaw, pitch, and roll of the device and relaying that information to the processor. This device utilizes land grid array packaging techniques with plastic encapsulant on top. The LGA packaging technique is a very important technique that lends itself to a lot of important characteristics for this packaging. This will be discussed later in the presentation. Another component found on the logic board from STMicroelectronics is the 813433DH00D35 3-axis accelerometer. This is the same as the STMicroelectronics LAS331DLH MEMS accelerometer, but has different markings. This component is an ultra-low power, high-performance 3-axis linear accelerometer. This device is concerned with detecting acceleration as part of the inertial measurement unit. Just like the previous sensor, this uses land grid array packaging techniques with a plastic encapsulant over top. Once again, this is a very efficient method of connecting this device into the larger logic board for the phone. Specifically, high mechanical reliability and better electrical performance are a few of the characteristics that this type of packaging lends to. Furthermore, the land grid array packaging technique is a very interesting type of packaging technique that was used both for the gyroscope and the accelerometer. This newer type of packaging technique has major benefits over the ball grid array. Specifically, it has a smaller profile and outline, which lends to a smaller volume. It has better electrical performance. It has better mechanical durability, and same board assembly process as ball grid array, which means it is easy to integrate and easily adapted into homogeneous integration. As you can see in the diagram at the bottom, an LGA module usually utilizes a flip chip device, but can use wire bonds and some other techniques. The smaller profile of these devices lends itself to smaller electronics and more room for other applications or heat sinking applications. In addition, this is an attraction for the consumer base since the devices themselves can become smaller. In addition to all this, this type of packaging has very good thermal performance as well. Heat sink planes on the bottom of the chip are very important for dissipating heat and allowing for proper power dissipation when needed. For all of these reasons, this is a very efficient way for these devices to be connected into the iPhone's logic board. The one major improvement that could be made to the ENME system is reducing the size of it. For instance, there are devices these days that integrate both the gyroscope and accelerometer into one device. These devices are a 6-axis device. A device, for example, that was used in the iPhone 6 and 6S is the MP67B 6-axis MEMS IMU. This is a modified MPU 6500, but has a different marking for the Apple iPhone specifically. This device incorporates the function of both of the devices that was in the iPhone 4S into one chip that is smaller than both of the components in the iPhone 4S. This system uses the same land grid array packaging techniques as the other components in the iPhone 4S, but is improved because of its volume reduction. As the volume keeps being reduced, the devices can become smaller and smaller with the components becoming smaller and smaller. The diagram below shows both the gyroscope and the accelerometer in one component. Although this diagram shows a Q&F lead frame finish, the MP67B 6-axis MEM IMU system that's actually used in the iPhone 6 and 6S uses a modified packaging system, which is the land grid array. Otherwise, both of these components are exactly identical.
iPhone 4S uses A5 CPU. CPU is a central processing unit which allows the device to execute multiple computer programs at once. Its performance is determined by the clock speed, which is 1 GHz for A5 CPU. A5 processor in iPhone 4S is made with Samsung's 45 nanometer manufacturing technology. Its dimension is 14 millimeters by 13 millimeters, and it costs about $25 to build. This is about $10 more expensive than similar dual-core chip used by Motorola Xoom. A5 processor is made up of package-on-package technology. It is a stacked chip involving the DRAM that uses solder balls to attach different levels. Key factors that contribute to manufacturer's decision are package-on-package allows high component density in device. It is a multi-core process for improved performance. Additionally, this specific design has efficient power management system with its variable clock speed. The photo on the right is an X-ray photo of A5 POP. 2 rows of dense dots around the edge are solder balls from memory chip in the top half of the package connecting with the bottom half. Less dense dots are solder balls on the bottom half of the package connecting the A5 chip to the device. First area of improvement to be discussed is the thermal reliability. The system reliability of a CPU is heavily dependent on the temperature, and it is significant in the 3D design due to high power density in the stacking arrangement. However, it was said from online sources that the possible thermal issues between the stacked up chips is inevitable. Another consideration of improvement is the size and cost. The new A5, which is 12 by 12 millimeters instead of 14 by 13 millimeters, that is used for Apple TV 2013, is made with Samsung's 32 nanometer process, intended to reduce the product cost. Likewise, the overall manufacturing method can be changed to reduce the chip cost. This specific RF transceiver includes both transmitter and transceiver, which allows the mobile device to send and receive RF signals. It is an improved version of RTR A600 with the same functionality. RTR A605 is a lead-free BGA packaging. This is the best information that can be retrieved from online, as there is not an available datasheet. This chip merges HSPA and CDMA radio capabilities into a single product, which were separately integrated. RTR A605 allowed iPhone 4S to be usable on multiple mobile network service platforms such as AT&T, Verizon, and Sprint. One consideration of improvement is that it is not running on 4G LTE network. However, this made iPhone 4S faster than the previous versions, but when having them side by side, the difference was not noticed as much. The device's wireless network performance can be improved with the implementation of a newer version of RF transceiver that is capable of 4G LTE network.
The Triquint TQM9M9030 surface acoustic wave filter, labeled blue on the left-hand picture of the iPhone 4S logic board, is used for data transfer purposes. Specifically, the WCDMA, or Wideband Code Division Multiple Access SAW filter's role is to filter the transmit and receive paths for a multitude of incoming signals, including 2G, 3G, 4G, Wi-Fi, Bluetooth, and GPS. The chip is manufactured using mainly monocrystalline silicon, aluminum, and epoxy resin on wafers for effective mass production at low cost. Additionally, SAW technology allows filters and duplexers for different bands to be integrated on a single chip with little or no additional fabrication steps. The TQM9M9030 is temperature compensated, meaning that its package includes overcoating of the IDT or interdigital transducer structures with layers that increase stiffness at higher temperatures. This presents solid performance under variable thermal conditions that are notoriously difficult for traditional SAW filters to handle due to their sensitivity. However, this also doubles the number of required mask layers, making the package more complex and expensive to manufacture. While the use of this SAW filter presents a number of advantages as previously discussed, it also presents an important limitation. Selectivity of incoming signals declines at frequencies above 1 GHz, and performance deteriorates significantly at frequencies above 2.5 GHz. In order to function efficiently at higher frequencies, a high-performance bulk acoustic wave or BAW filter would be a better option. Unlike in SAW filters where acoustic waves propagate through the package in a lateral direction, the waves propagating through a BAW device travel in a vertical direction. This allows BAW filters to isolate incoming signals at frequencies of up to 9 GHz. The BAW design is also much less sensitive to thermal conditions, eliminating the need for the TC treatment. While the cost of fabricating BAW filters remains higher than that of TC SAW filters, BAW devices are fabricated on larger wafers, so about 4 times more devices can be harvested per wafer. In fact, Apple decided to incorporate the use of several BAW filters in the iPhone 6s, including the Qorvo TQF6405 and the Avago AFEM8030. The Triquint TQM666052 duplexer module, labeled pink on the left-hand picture of the iPhone 4S logic board, provides excellent RF performance with low current consumption, resulting in longer talk times in portable applications. The 3.5 by 4.5 by 1.0 mm package is ideal for slim, lightweight mobile phones. The module's main function is to allow transmitters and receivers operating at different frequencies to share the same antenna. The TQM666052 has 2 bandpass filters connected in parallel. One provides a path between the transmitter and the antenna, while the other provides a path between the antenna and the receiver. The TQM66652's land grid array or LGA surface mounting technology is clearly visible in the upper right-hand figure. LGA technology presents a number of advantages over traditional BGA applications, many of which were previously described. Several of these benefits are particularly applicable to the TQM666052's bolstered RF performance. Notably, the unique layout of the ground pads underneath the RF components minimize the impact on antenna path, thereby further improving flexibility, reliability, and durability. In traditional BGA technology, residues of flux lead to passivation, or reduced conductivity of the balls. Residues of flux on module ball surfaces can reduce the yield rate and pending performance of the module. Both Triquint chips in the iPhone 4S appear to have similar functionalities and could be combined into a single package to provide more retail space on the logic board. This appears to be an improvement made in the iPhone 5 with the Triquint 666-083-1229 pictured in the bottom right-hand corner.
TI 343 SO538 touchscreen controller. The TI 343 SO538 touchscreen controller TSC is manufactured by Texas Instruments with a part number F761530. This controls the signals sent from the capacitive touchscreen to produce a response accordingly. Let's talk briefly about how the TSC or the touchscreen controller works. The touchscreen controller functionality of the iPhone 4S is achieved by the TSC and a display driver IC. Both parts are made of silicon and are usually made by 2 different companies. The IC of the TSC continues to monitor the screen for a touch as it is in the low current mode, and when the screen is touched, the IC performs analog to digital conversions to determine the location of the touch. It then stores the X and Y locations in the registers and then issues an interrupt. This process is repeated over 100 times until there are no more touches to be detected, in which case the IC switches to low power mode again. Now, talking about the design selections of the components, the TSC uses a flip chip technology as shown in the figure at the bottom as a way of increasing device performance by decreasing electrical propagation delay. The IC is surface mounted to the printed circuit board by ball grid array BGA, which is shown in the figure at the top right. Given the size of the IC, this is a chip scale package which helps to reduce the overall size of the phone. The device is also overmolded and rigid substrate base to provide mechanical reliability to it. Generally, iPhones are known to be highly vulnerable to touch diseases. Most of the iPhones experience touchscreen problems, rendering the phone useless after a couple of uses. This could be as a result of the location of the IC placement in the phone or manufacturing flaws. Therefore, the least drop of the phone poses problems to it. And this is the area that needs to be improved, and so relocating the IC to low mechanical stress areas will prolong the life and functionality of the touchscreen controller. Also, using a flexible interposer based CSP would help in absorbing the shock from falling. TSVs through silicon vias can be incorporated into the design to improve electrical performance and also reduce package size, although this may be a little more expensive. Heat sinks at the top of the chip or thermal vias can also be created to help in thermal management. I must say that there was not enough information available about the zeroth and first level design and interconnections, and I think this must be top secret of the company. Moving on to Apple 338 SO987 audio chip. The Apple 338 SO987 sound IC shown on the figure at the top is an ultra low power stereo with headphone amplifier manufactured by Cirrus Logic with a part number CS42L53. This chip is responsible for controlling all sound quality in the iPhone 4S by a digital sound technique. And the IC goes through about 5 steps to store and process digital music. And these steps include sampling and holding of the data, analog to digital conversions, digital signal processing, digital to analog conversion, and then filtering. The audio chip has about the same design choices as the touchscreen controller. It has flip chip technology as a way of increasing device performance by decreasing electrical propagation delay, and surface mounted to the printed circuit board by ball grid array, which is shown in the figure at the bottom left. It also has a chip scale. It is also a chip scale package, which helps to reduce the overall size of the phone, and it's also overmolded and rigid substrate base to provide mechanical reliability to it. According to some users, this new audio chip has inferior sound quality compared to its old counterpart CS42L61. The new audio chip was made to produce or to reduce power consumption by the device. However, the attempt to reduce energy consumption has affected the quality of the sound. Therefore, one area that needs to improve is thermal management as the quality of the sound is being perfected. Creating heat sinks or thermal vias can also be useful in helping with the thermal management of the phone. This project provided us with an opportunity to explore more about microelectronic devices and their packaging techniques or technologies. and also to apply knowledge gained from class to real world devices. It also helped us to know how fast packaging technology is changing as more and more complex devices requiring even smaller space yet more functionality becomes a thing of interest. It has helped us to know why certain technologies as opposed to others in terms of material functionality, reliability, efficiency, and so on are being used today. The iPhone 4S is a relatively small iPhone in terms of the packaging technologies used, and the emergence of new phones with new packaging technologies is almost fading the iPhone 4S away from the market. And because of this, it makes it difficult to find information about the phone's packaging technologies that was used. And I think another reason to the lack of information could also be that it is a top secret, as I said earlier, of the iPhone company. So this is the end of our presentation, and thank you for listening.